that the direction of the current has been reversed. Initial condition. Well, in all the previous examples which we have done so far, we have assumed that the capacitors were uncharged, that is, the voltage across the capacitor was equal to 0 when the switch was connected to the source. However, in the next example, we will see that a charge is already present on the plates of the capacitor at the instant the switching action takes place. That is, the voltage across the capacitor at that instant will not be equal to 0. It will be a finite value. And that voltage is known as initial value. This is expressed or shown over here in the general waveform. Initially, during the charging phase, the capacitor's exponentially rising voltage graph would start from this point because initially the voltage across the capacitor was 0 in the previous examples. In this example, we are considering that a small amount of voltage is already present in the capacitor. Hence, when the switching action takes place, the charging phase graph will start from here and will move towards the supply voltage level. This time period is known as the transient response. And from this point onward, the steady state region will start. And from this point beyond, the initial conditions exist. Using this information, the expression for Vc would be the voltage across the capacitor can now be expressed with the following equation. We know that Vc equals E times 1 minus e to the power minus t by tau. In this case, E will be equal to Vf minus Vi. Rearranging these terms, we can define Vc as Vf plus Vi minus Vf e to the power minus t by tau. In this example, the capacitor has an initial voltage of 4 volts across the plates. Now, we have to determine the mathematical expression for the voltage across the capacitor once this switch is closed. Then we need to find the mathematical expression for the current during the transient period, and we need to sketch the waveform from initial to final value for both the voltage and the current. Now, the capacitor has a voltage of 4 volt across its terminal. The switch is closed and now the voltage across the capacitor will increase from 4 volts and will be equal after the transient period will be equal to the supply voltage, which is 24 volts. This network has two resistors connected in series, that is R1 and R2. Thus, the time constant is determined by using both R1 and R2. That is, tau equals R1 plus R2 times C. In that case, tau will be equal to 11.22 milliseconds and 5 tau will be equal to 56.1 milliseconds. Now, applying the equation, we know that Vc equals Vf plus Vi minus Vf e to the power minus t by tau. Using the values which we have already obtained, the equation for Vc will be equal to 24 volts minus 20 volts e to the power minus t by 11.22 milliseconds. Since the voltage across the capacitor is constant at 4 volt before the closing of the switch, the current must have an initial value of 0 milliampere because the loop is not completed until and unless the switch is closed. At the instant when the switch is closed, The voltage across the capacitor cannot change instantaneously. So the voltage across the resistive elements at this instant is the applied voltage, which is less than the initial voltage across the capacitor. The resulting peak current is Im equals E minus Vc divided by R1 plus R2, which is equal to 5.88 milliampere. Using this value, we can determine the expression for IC, which will be equal to 5.88 milliampere e to the power minus t by 11.22 milliseconds. The sketch for the graph of voltage against time and current against time is shown over here.